This week we're going to continue our discussion of electricity and magnetism and electromagnetism. And this week we'll really see why we call it electromagnetism. And that is that electricity and magnetism are intimately related. That we'll see that electrical effects can cause magnetism and vice versa. So just to go through a little bit of the history, up until about the 1800s, electricity and magnetism were thought of as two separate effects. And if you think about what was going on at that time, this is before the battery had been invented, before there was any electrical power distribution at all, so that really the only electrical effects that the average person would have been familiar with would be lightning. And that seems pretty different than what happens when you take two magnets and bring them near each other. Now, magnetism was definitely more well known at that time because compasses using the magnetic field of the Earth were used for navigation. So magnetism was well known. Electricity, not as much, was known about it. And really, they seem like two completely different things. The first progress towards understanding the connection between electricity and magnetism came with the ability to generate an electric current. We've talked about what current is. It's the flow of electrons through a wire. And in order for there to be a current, we need a source of energy or electric potential. And the battery is certainly one source. And then, of course, nowadays we have our wall outlets that we just plug into. But the battery wasn't invented until about 1800. And that's when Alessandro Volta produced the first working battery. And once we had the battery, then we could actually have current flowing through a circuit. The unit of electric potential is called the volt, and we can see that that's named after Alessandro Volta. And electric potential is what a battery or the wall outlet provides. Another name that's sometimes used is electromotive force, but electric potential is really the name that we mostly use. And electric potential just means it's a source of voltage. It's the energy that powers the circuit. So let's take a look at the first evidence that electricity and magnetism were connected. Hans Oersted was the first person to see this connection. And here's what he did. He set up a wire. He set up a simple circuit. You'll notice we've got a battery to provide a current. And when we close the switch, a current is going to flow in the wire. Well, what he found was that when there was a current flowing in the circuit, a nearby compass changed direction. And what that implies is that a current produces a magnetic field. Now, we already have talked about the fact that anytime you have a charge that's in motion, it induces a magnetic field. And so now that we understand that current is just electrons flowing in the wire, it makes sense that as electrons flow by in the wire, it's creating a magnetic field. So that connection was first found by Hans Oersted, and that was the first important link between electricity and magnetism. To look at that in a little bit more detail, the magnetic field lines produced by a current in a wire form concentric circles. And the way we would see this, there are a couple different ways, and I'm going to demonstrate a number of these things to you in class. But for example, if I take a compass and I hold it near the wire, what we'll find is that the north pole of the compass points in the direction of the magnetic field. And so if I put the compass in this location, the compass would point like that. If I put the compass right here, I would find the North Pole pointing this way. So, in other words, the compass is always going to orient itself so that the needle of the compass points in the direction of the magnetic field. There's a way to keep track of what the direction of the magnetic field is from a current-carrying wire. And what we do is we take our thumb and put it in the direction of the current, and then our fingers give us the direction of the magnetic field. So if I put my thumb in the direction here of the current, then my fingers curling around would show me the direction of the magnetic field. Now, oftentimes when we want to create a magnetic field from a current-carrying wire, we want to actually create a strong magnet. And in order to do that, we need to concentrate the magnetic field that's created. The easiest way to do that is to simply take our wire and form it into a coil. And a coil of wire is called a solenoid. If we look at the magnetic field that's created by a solenoid, the magnetic field is actually strongest right in the center of the solenoid. So that gives us a way to create a very strong magnetic field. And if we want it to be stronger, we would just increase the current in the coil. Now, if we look at the magnetic field coming out of the coil, if we look at outside the coil, it really looks just like the magnetic field of a bar magnet. In other words, if we look at the magnetic field of a bar magnet, we'd see that it looks something like that. And you can see that it's very similar to the magnetic field created by a solenoid. And I'll demonstrate that for you in class. So once we have a coil of wire, we can now make a very practical electromagnet. And an electromagnet is simply a coil of wire that usually is wrapped around an iron core. You may have done an experiment like this at some point in your schooling, and that is you take a nail and wrap wire around it. And when you put a current through that coil, it magnetizes the nail. In other words, it's creating an electromagnet. And if we increase the current or we increase the number of coils, we can increase the strength of that magnet. Commercial electromagnets can be exceedingly strong. For example, in junkyards, they can actually lift cars with electromagnets. So we can get a very strong magnet using an electromagnet.